All right, we have number 23 here, where we have a geosynchronous satellite that's orbiting at an elevation, this is above Earth's surface, of 3.59 times 10 to the 7th meters. Right? We'll learn later when we study Kepler's laws and uniform circular motion why that's the elevation, or that's the height, the altitude at which it'll rotate. But for now, just accept that that's true. It told you that's where it is, the problem there. All right, now, we also know that we have a distance of 6.38 times 10 to the 6 additional meters to Earth's center, right? When we're solving gravitational problems at magnitudes of gravitational acceleration, we are center to center, right? So the total distance is going to be the sum of those. The total distance between them, r, is going to be the sum of 3.68 times 10 to the 6 and 3.59. So what are we getting? We're going to get 3.59 plus 0.63. So it's going to be 10 to the 7th, 4.2-ish. What does it turn out to be? If you add these two, someone please? Just do it myself. 638. All right, 3.59, and then 638, right? Because that's times 10 to the 6, right? So we get 8, 9, and 3 is 12, 2, 4.228 times 10 to the 7th is our total distance, right? Is that what we got? It's our total distance out to the satellite, okay? That's what we'll use for R. Okay, so now, gravitational acceleration, I want you guys to remember this. Remember, mg, this is in general, for any object, mg is its weight, correct? Weight is its gravitational force. Mg is weight, gravitational attraction. A gravitational attraction can also be expressed as g, the gravitational constant,
M1
times m1, m2. But we'll say m for mass of Earth, and little m for the mass of the satellite. This is the weight of the satellite, this m, the weight of the satellite, mg here. This is the mass of the satellite, divided by r squared, our new r, the one we just came up with. Okay, so m's cancel out, so g is gravitational acceleration, right? Remember, if you put Earth data in for this, Earth's mass and Earth's radius, you'll get 9.8 meters per second squared. Okay? Does that sound familiar? Remember doing that before? Okay, so now, that's what gravitational acceleration is. That's the problem, right? Okay, so all we have to do now is put all this stuff in, all right? G, our gravitational acceleration, there's going to be 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. That's G. Mass of the Earth, 5.98 times 10 to the 24th kilograms. All right, and then divide all that by r squared, which you said 4.42. All right, 4.23. 4.23 times 10 to the 7th meters, and that's squared. All right, so there's a little number crunching to do there, but let's first check all of our units. All right, and the units should turn out to be right. Newtons is kilogram meters per second squared. So let me see what we get here. Wow, a lot of messing around. All right, so meters squared on the top, cancel out these meters squared down here, but we're still going to have to square this right here, right? So this gets rid of one of these, right? Kilograms, so we have newtons over kilograms. That should be meters per second squared, right? Okay, so checks out. So because newtons here is equal to kilogram meters per second squared, newtons here divided by these kilograms is equal to meters per second squared. All right, as always, dimensional analysis is as troublesome as the whole problem itself. So when we crunch all these numbers together, that's just the answer for the problem we're looking at. So anybody do that? Don't forget to square what's on the bottom. Sky, did you come up with something?
I did, but it's wrong.
All right, still waiting. So G turns out to be 0.229, so 0.223 meters per second squared. Okay? All the way out there, not nearly as much gravitational acceleration. Okay?
FG is mg.
The force of gravity is mg. That is correct.
Okay.
Yep, that's the whole thing is predicated on setting these two things equal to each other. Okay? Right there. That's
Do
the
you feel that like gravitational